So now you are with me, known as Damayanti Zakaria, metric number 153604. The selection of median MPH and exposure time, collectively known as MAS, directly affects the total quantity of radiation produced during an exposure. Proper MAS selection is one of the most effective ways to yield properly exposed radiograph and reduce patient dose. It is then important to make sure that the amount of time that radiation is being emitted from the X-ray tube match the time selected by the operator. Therefore, it is critical for the exposure timer to be accurate and properly calibrated. Exposure is the amount of radiation striking or passing through the film. Exposure is equal to the product of the radiation intensity at the film and the required exposure time. Radiation exposure can be accumulated over the time of exposure. For example, in C-arm fluoroscopy guided interventions, the time spent checking the C-arm fluoroscopy is related to the radiation exposure. The longer the exposure time, the more radiation exposure to the pain physician. Therefore, it is important to reduce the time of C-arm fluoroscopy. To reduce the usage time, the physician has to improve his skills in intervention and the radiographer has to check the X-ray at the correct location and at the right moment without blurring the image. Exposure of a radiograph can be set manually by choosing tube current and exposure time, except in examinations with little variability in body dimensions, for example, extremities. An AEC, automatic exposure control, is mandatory to achieve a consistent image quality or film density. The AEC terminates an exposure when the image receptor has received a present level of radiation. The AEC system consists of 1 to 3 radiation detectors, ionization chambers or solid-state detectors. The signal from these detectors is amplified and integrated, corrected for response in photon energy and dose rate, and finally compared with the present dose level. The exposure is terminated when the chosen level is attained. In case the AEC does not terminate the exposure, a backup timer sets a time limit. On installation of a radiographic unit, the dose levels are set, taking into consideration all the components of the imaging chain, for example, film and screens, imaging plates, film development, preferred tube voltage and filtration, acceptable image noise, and etc. This process needs to be carried out for all tube voltage, image receptor, and examination types in question. Some products allow for fine manual adjustment to be preset dose level by a density control on the console, adapting the density in steps of 10 to 20%.
Hi everyone, my name is Caroline Priscilla Timor and my metric number is 152039. Okay, now I will share about the test equipment that needed for exposure time accuracy, which is have 4. The first one is the synchronous top. The second one is lead blocker sheet, which is to permit exposing the tested one lesion at a time. Okay, the third one is step wedge, which is 6 level of Cooper, and the last one is cassette.
The definition of exposure time accuracy is, this test produce describe the use of spinning top to determine the accuracy and the reproducibility of timer sitting on single phase, 3-phase and constant potential radiographic X-ray units. For the purpose of this test produce, accuracy will mean the degree of agreement between the measured and indicated time values. Reproducibility will mean the degree of agreement between several measurements of the exposure time at the same indicated time on the X-ray control panel. The manually energized top will not measure exposure time on 3-phase or constant potential X-ray units, since the resulting radiograph of the whole or split will show a solid arc. However, if the top were rotating at non-speed, then the angle defined by the arc would be directly proportional to the exposure time. a top which rotates at non-speed at the time of exposure and which can be used to measure exposure time on all types of X-ray units is referred to as a synchronous stop. The manually energized synchronous stop is spun by hand and its rotational speed is known by observing the repetitive pattern on the upper surface of the top.
Do we use phantom to test time exposure accuracy? Do you know what is phantom? Measurements using phantoms are useful for the control of technical parameters, including equipment under automatic exposure control, the comparison of the same system at different times, the comparison of different system, optimization of individual components of the imaging system or of the whole system. However, they cannot provide a direct estimate of the average dose for a given patient population or the variation that occurs in practice because of variations in patient size and composition. They also provide no information on how technique factors may vary with the operator. It is important, therefore, that measurements made using phantoms are complemented with measurements made on patient, though the measurement frequency will be different for the two types of measurement. Phantoms vary in degree of complexity and anatomical accuracy. Generally, the more realistic they are, the more expensive they will be. But, do we use phantom to test time exposure accuracy? Do you know what is phantom? Measurements using phantoms are useful.
In this test, we are not using phantoms.
Hello everyone, my name is Kitiapa Anak Pemul Pratjum and my metric number is 153860. So today, I'm going to explain about standards. First of all, important factors to be considered in determining the exposure time. The time frame, which are induction and latent periods, changes in exposure status or exposure to other therapies, and consistency and accuracy of exposure measurement. Next, let's look at reasonable range of acceptable timer accuracy error. This is just an additional information about range of acceptable timer accuracy error. According to Safety Code 35, the actual time of exposure should be within plus minus 10% plus 1 millisecond of time selected by the operator. Similarly, according to the Healing Arts Radiation Protection Act, the actual time can deviate from the selected time by no more than plus minus 10%. Now, let's focus on our topic today, which is about exposure time accuracy on quality control. The Wisconsin timing and milliampere seconds test tool is both easy and quick to use to determine the accuracy of the exposure timer. The accuracy and consistency of short exposure times is important since a small error in exposure time could be larger than the set exposure. For example, if for a set exposure time of 0.01 there is an error of 0.01 second, this represents a 100% error. However, this same 0.01 second of an exposure time on 1 second represents only 1% error. The test tool contains a brass disc, the rotation of which is controlled by a synchronous motor. Because of this, it is suitable for testing single-phase and three-phase units as well as capacitor discharge equipment. The disc has two slits near the perimeter which are spaced 1,800 apart. Each slit subtends an angle of 2, and this finite slit width must be taken into account when assessing exposure time in three-phase and capacitor discharge units. The brass disc rotates at 1 revolution per second, and so can be used to determine timer accuracy for exposure times up to 1 second. In addition to the disc and synchronous motor, the test tool also houses a copper step wedge to allow relative milliampere value assessment. A given milliampere second should produce the same density in the image for a set kilovolt irrespective of the milliampere used. This can be checked by comparing step densities in the image produced at different milliampere values for the same milliampere second and kilovolt. It is possible to combine both milliampere and exposure time assessments by careful choice of exposure values. The manufacturers recommend using 80 kV for testing single-phase units and 70 kV for three-phase and capacitor discharge units. When both milliampere calibration and exposure timer accuracy are assessed together, the appropriate kilovolt is selected and milliampere second value chosen by trial and error to provide a reasonable step range image. Moving on, let's see how it worked. In a single phase unit operating on a 50 Hz main supply, there will be one distinct pulse of useful radiation, which is image density forming every 0.01 second. These pulses will be imaged as separate slits around the periphery of the disk image. Each slit image represents a time of 0.01 second, and just counting the number of such images and multiplying by 0.01 gives the total exposure time in seconds, providing it is not a self-rectified unit. For the short exposure times of less than 0.1 second, the number of pulses should be exact. For times longer than this, a small error of 1 or 2 in the number of pulses is acceptable, where the pulse images are so close together that they are impossible to distinguish separately in the case of 3-phase 12 pulse. Since the slit is of width 2 degree, then the arc produced will be 2 grade by 20 degree. This must be subtracted from the angle measured for the arc before calculating the exposure time. Determination of exposure time is straightforward. The disc rotates at 1 RPS. So for example, in 360 degree in 1 second. So for an exposure time of 0.01 second, for example, the arc angle measured will be 0.01 multiplied with 360 degree, then plus with 2 degree, and then we will get the answer 5.6 degree. Thus, to determine the exposure time value, in this case, it is only necessary to measure the angle subtended by the arc and use the formula that I already attached below. That's all from me. Thank you.
Hello everyone, my name is Alfabeta Binti Jami with matrix number 153875. Today I will explain to you guys about the QC method. So everyone, what we need to use in this QC method is we need to use 80 kVp to determine the MAS and distance for our film screen processing combination to produce a useful radiograph of the synchronous stop on the X-ray unit to be tested. Everyone, I will explain more detail about this test procedure so you will be more clear about what you need to do in this QC method. First, what you need to do is for motorized synchronous stop only, you need to plug the top into an electrical socket and ascertain that it is functioning. Second, you need to place the synchronous stop and optional step wedges in region 1 and cover the unused portion of the cassette with the lead blockers. Third, you need to select the appropriate distance and adjust the collimator so that the beam dimensions just exceed the dimensions of the region in. So everyone, after you have done select your appropriate distance, you need to select the timer testing to be tested and record this time on the datasheet under the column mark indicate time and across from the number of regions currently in use. Then you need to set at the kVp and the MA necessary to approximate the previously determined MAS for this unit. After this, for manually energized synchronous stop only, you need to place the top on the cassette and cause the synchronous stop to commence rotating and observe from the control booth until desired rotational velocity if achieved. After this, you can make your exposure. Next, move the top to the next area of the cassette. Repeat the appropriate steps 1 through 6 for different time values until all the regions of the cassette have been exposed. If possible, all exposures should be made at the same value of MAS when the step wedge is used. Then, you need to process the exposed film. Last but not least, on the process radiograph, immediately record the data and room number and transfer the indicate time from the datasheet to the corresponding regions on the radiograph. Then that's all on this QC method. I hope after this you will be more clear what you need to do to make sure the exposure time is accuracy. Then after you have done with your QC method, you can make the calculation that have been explained on the standard part.
As mentioned before, the accuracy of the timer plays a crucial role in reducing patient dose. An exposure that lasts longer than it should only expose the patient to unnecessary radiation, which result in an increased patient dose. An improperly calibrated timer could also cause underexposure if the duration of exposure is shorter than it should be, and overexposure if the duration of exposure is longer than it should be of radiograph. In a digital environment, these problems could be corrected, but there can be cases where the resulting radiograph cannot be processed into a diagnostically acceptable image. Should problems of underexposure and overexposure arise in a film or screen environment, a repeat X-ray should be absolutely necessary, which again increases the dose to the patient. Also, if the timer is suspected to be malfunctioning, corrective action should be taken immediately. The quality control test allows technologists to apply the ALARA, which is as low as reasonable achievable principle effectively and accurately when performing any type of radiographic examination.